Welcome back. We got another one going here. And yeah, we're going to start off with a little bit of story time from Mr. Slagle. I'm going to tell you guys a story. It's going to be an autobiography. I'm going to draw a little graph right here once I get my pen working. Classic. This is a story about Mr. Slagle. This right here is the instant. The x-axis is going to be my age in years. Okay. The y-axis is the amount of money that I have saved. Ultimate goal is Mr. Slagle would like to retire from the teaching profession at some point. Retire and live out my days in my hobbit hole, eating various cakes and teas. But that's besides the point. Mr. Slagle wants to retire, and every quarter, I get a letter from the state that says, "Hey, Mr. Slagle, if you retire right now, you're going to receive $12.78 for the rest of your life." Now, I don't know what's more concerning, the fact that I'm only receiving $12.78, or the fact that the state retirement has determined the moment of my death, because that is, what do they know that I don't? Okay, I've seen the future, and I know that I die right about here. Is this getting too dark? All right, this is me. Okay, that's me when I die. Now, in a perfect world, Mr. Slagle's savings is not linear. I should be, how much I'm saving should grow over time because of interest, and I'm getting pay raises because I'm such a great employee. And over time, the amount of money in my bank account should be going something like this. We're going to assume that my savings is roughly linear. Okay, if I was a vampire and I were to work forever, that would continue to go that direction. But then I also have, ultimately, you want to retire, and so once you retire, your income is from what you've saved, right? And so you are collecting on your income, and you're spending that money that you've saved, and you're spending that at a certain rate. So you're earning at a certain rate, or assuming it's the same, it's actually not. And then you're spending at a certain rate, and ideally, I will spend all of my money, I'm going to spend all of my money and leave next to nothing to my family. I'm just kidding. I'm kidding. I want to leave something for my family, but let's say that's the case mathematically for what's happening here. What that means is I have two separate equations, right? I have two separate equations. One that describes my earnings, one that describes my spending after I retire. If I know how fast, or have an approximation of how fast I'm going to spend my money after I retire, well, then we have this very interesting point right here to talk about. This is the moment, the instant in my career in which I will no longer be allowed to come to school because I'll be retired, right? This will be my age of retirement. It's a point, right? It's a point in my life, and it's a point that has to do with my age, but also the amount of money that's in my bank account. The longer that I wait, the more I'll have in my bank account, but the less I will need, because I shouldn't be alive as long, right? The age of retirement, this is the money in savings at that time, right? My money in savings at that time. So that's my point of retirement, in which I'm no longer generating income. And so we can think about these two equations. We can see that when they cross, there's a story to be told, okay? The reason I'm telling you this story, and I've been going on for 4 minutes, is that systems of equations have a purpose. They tell a story, and they give us a moment in time or space that we're interested in. So when I'm doing these really dry examples that don't have any meaning, I want you to think back to this example that I'm talking about right now. About me planning for my future, about me being able to retire one day, and knowing, hey, I've been thinking about what do I want to live like? How much am I going to spend when I retire? And how long do I want to work? Those are serious questions that that algebra can answer. That's pretty exciting. So let's go ahead and jump right in here with a system of equations that we can take a look at. What do you think it means for a number to be a solution to a system of equations such as x plus y equals 10 and x minus y equals 2? Can you think of the solution to this system? Now I'm going to invite everybody watching this video, even those in the background that are trying to do something else, take a look at this system and see if you can figure out which two numbers add to 10 and have a difference of 2. I bet you can figure it out. Okay, on your mark, set, go. All right, so hopefully you have it now. It is it? 6 and 4. Now 6 has to be the x value and 4 has to be the y value. This is the only ordered pair, x comma y, that will make this set of equations true. Okay? So what does it mean for a number to be a solution to the system of equations? It has to make both of them true. So when you plug in x and y, 6 minus 4, you can check, 6 plus 4 equals 10, right? 10 equals 10. We can check to see that this is true. Okay, and then we can do that again. You check with the bottom equation. So if you plug in here, it's 6 minus 4. Is that equal to 2? Of course. Yes, it is. 2 equals 2. Okay, so you have to check and make sure that both equations are true. If you plug into one and it's true, it doesn't necessarily mean that that's a true case. It doesn't necessarily mean that it's a solution to the system. It has to be true for both equations. So what this means when we're checking, when we plug in an x and a y and we see if we get a true statement, it really means that this point is on the line, right? 6, 4 is on the line, x plus y equals 10, and 6 comma 4 is on the line, x minus y equals 2. So since these are two linear equations, these actually cross at one spot only on a coordinate plane, but the point that they cross is the only point that lies on both lines. So getting a true statement means 6 comma 4 is on this line, is on line 1, and 6 comma 4 is on line 2, which is pretty exciting. Now remember, just a quick recall, when you're solving a system of linear equations, there are only 3 possible ways that those equations can interact. They can interact by crossing once, they can interact by not crossing at all, or not interacting at all. That would be parallel lines, so there would be 0 solutions in that situation. And they can interact, they can interact by being the same line. And if they're the same line, they cross everywhere. You have an infinite number of solutions, but we went over that in a previous video. So here's what I want you to do. I want to use the method that I just gave you. I want you to check the next system and see if it's a solution. On your mark, get set, go. Do this on your own, don't watch me. Just do everything, try it for yourself, and then try it again if you make a mistake. Okay, let's see if this point is a solution to the system. Plugging it in, 5, x goes in for x times 8 minus 4 times 5. Is that equal to 20? We're checking the first equation here. So I'm plugging in 8 for x, 5 for y, and we get 40 minus 20. Is that equal to 20? And of course, yes, it is. Woo! So that means 8 comma 5 is on, that's ugly. 8 comma 5 is on line 1. Let's check the second one now. Is, oops. 3 times 5 is 3 times 5 equal to 2 times 8 plus 1. Well, let's take a look. 15. Is 15 equal to 16 plus 1? 15 is not equal to 17. So that means that 8 comma 5 is not on line 2. Now, since this one was a smiley face and this one was a frowny face, it was on this line, it wasn't on this line. Is this a solution to our system? Not. 8, 5 is not a solution. Not a solution because it needs to be on both. Since we had one fail, one or both, if one or both fails, you got a problem. That's exciting. Okay, let's do some graphing. With most systems, guessing and checking is not a good way, right? So like just plugging in points, sitting there and plugging in, trying to find, probably not a good idea. What I would recommend, right, is to probably graph or use some algebra. We're going to see 2 methods today in class, and I'll tell you what, I'm starting to get excited. Okay, system of equations for the next couple lessons, just made up of 2 linear equations. If we graph these linear equations and we find where they cross, we've found the solution to our system. So we just got to graph them, we got to see where they cross, and then we're good to go. Here we go. Alright, in blue, in the blue corner. Oh, what? That's like not ready to graph. What a drag. Let's not do that one yet. In the red corner, being much simpler to graph. Okay, we're going to graph y equals x minus 2. That's got a slope of 1 and a y-intercept of -2. So I'm going to start at -2. It's got a slope of 1. 1 is a fraction. Remember, is 1 over 1. Go up 1 over 1. Should be going to the right. I'm not going to explain any more graphing for the rest of this video. So I'm just going to kind of run through it quickly. All right, so here's our line. There's the red line, and let's do the blue line. Blue line, this is a little harder for graphing because it's not in slope-intercept form. It doesn't say y equals mx plus b. So we're going to have to make it say y equals mx plus b, which means I want to isolate y, which means I got to move x to the other side, so we'll end up with 2y equals -x plus 8. And to solve for y, I want to get y by itself. We'll multiply it by 2, divide by 2 on both sides, and you'll get -1/2, 1 divided by 2, and 8 divided by 2 is plus 4. So we're starting up here. We got a slope of -1/2. We're heading down like so. And there we go. We can actually kind of stop graphing there because we found where the 2 lines cross. All we have to do... I did it. I did it, Mom. I did it. They crossed. Alright, now let's take a look. Our solution is the point where they cross. So our solution, you need to state the point. If you just graph it, that is not sufficient. You need to state that the solution is 4, 2. Okay, that's our solution. 4, 2. Here we go. Next one. Feel free to pause the video and try these on your own. I'm just going to keep on trucking. Blue time. Alright, so for this one, not in slope-intercept form, but it's real easy. All we have to do is move that term over. So it'll be y equals -2x plus 5 to isolate y. That's what we're interested in. -2x plus 5. -2x plus 5. Apparently, my house is full of crazy monkeys. Crazy monkeys. In red. Got to solve for y, which means we're going to add x to both sides of the equation, and we'll get y equals x plus 2. Y-intercept of 2, slope of 1. And here is our wonderful, just peachy wonderful red line. All right, and then we're going to come over here, and our solution is the point where they cross. Draw an arrow to that point. It is the point 1, 3. And there was much rejoicing. Okay, you guys try these next two on your own, and you think you're going to find some interesting results. Remember, when we graph two lines, the solution to the system is where they cross. All right, here we go. In blue. In blue. In blue, the top equation, all I got to do is subtract 3x from both sides, so you end up with y equals negative 3x plus 5. Fun. This is fun. Okay. And the red line. We're redlining it, team. I want to get 5y by itself so I can divide by 5, which means I'm going to subtract 15x from both sides. And you're thinking, we can't subtract these. Oh, I know. I know. So we're going to write it as 5y equals, these are not like terms, negative 15x plus 30. I want to divide by 5 to solve. Oh, that's kind of hard to read. Whatever. 5 divided by 5 is 1. 15, that's going to be negative 3x. Negative 15 divided by 5 plus 6. So coming over here, that looks like this. Now these two lines are very, very close, but they have the same slope. Since they have the same slope and they have different y-intercepts, these lines are parallel and they are never going to cross. And if they never cross, there is, wait for it, no solution. There is no solution because these are parallel lines. No solution because they are parallel lines. Exciting. We're getting there. In the blue corner. Oh, this one's already in slope-intercept form. Sweet. 2x plus 3. I am so good at graphing. Look at this. Grammy is up there raising heck. Okay, we want to solve for y. Get the y term by itself, which means we're going to add 4x to both sides. And you'll get 2y equals 4x plus 6. Solving for y, that's what we're interested in. So we're going to divide by 2, similarly to what we did in the previous example. And we'll get y equals 2x plus 3. Oh, wait a second. That's the same line. Since this is the same line, these two lines cross everywhere. So what we say, a lot of students, so the answer we'll say is there are infinite solutions. There are infinite solutions, but please don't say all real numbers because it's not every point. You can't say all real numbers because it's not every point that's a solution. There is a definite number, or there is a select set of points that are the solutions, but there are infinite number of them because they cross everywhere. So we can list some of the solutions, like 0, 3 is a solution. 1, 5 is a solution. 2, 7 is a solution. Okay. So is this one, I think, right here. Yeah. So any point on the line on these lines is a solution, but it's not. Like, this point's not a solution because it's not on the lines. Hopefully that makes sense. So you just say infinite solutions. You don't have to list them all. Okay, great. Okay, when two things are equal, they can replace one another. So now we're moving into a different technique for solving a system. Okay, so systems can be solved graphically, and in fact, that's usually what I would do. I would use some sort of software to graph to solve a system. But you need to know that if you're graphing by hand, right? If you plan to graph by hand and you're looking at a graph, it's not always useful. Like, for example, in situations like this. Let's say our two lines cross right here. Okay? Let's say our solution is right there. Now, it's not obvious. Do you actually know that it crosses at a half? And what is that? Like, we don't know what the point is. So graphing has its limits because if you're not using a computer and you're trying to do it by hand, you can't necessarily always see an accurate solution. You get an approximation, that's fine. But if you want to get the exact answer, algebra is probably the way that you should go. Okay, and so what we're going to do is we're going to do the next set of examples using algebra and not graphically. So when I ask you solve the system algebraically or using the substitution method, you need to use that method, and you can use graphing to check your answer, but your math should show the answer, the substitution. So it says two things are equal, they can replace one another. So we can replace or substitute one expression in this for another. So the substitution process has kind of 4 steps. Okay, step number 1 is to isolate either x or y. That means get x or y by itself, and this is already done for us, right? It's already done for us because y is by itself right here. So step 1 has already been completed. Step 2 in the substitution process is to replace the variable from step 1. So what you do is, and I'll say in the other equation. So check this out. So what I'm going to do is I'm going to rewrite the other equation. So this is the one where we isolated y. It's already isolated. I'm going to rewrite this equation. We're going to write it like so. 7x minus 2. And then I'm going to put empty parentheses. And the reason I'm doing that is because I'm going to take this y equals negative 2x plus 4. I'm going to take this equation. Since y is equal to this, I can replace y in the second equation with negative 2x plus 4, right? So what I'm going to do is, instead of writing y, I'm going to write what y is equal to. Y is equal to this, so I can substitute it in. And anytime you substitute, you always want to use these empty parentheses. Okay, and that is going to move on to step 3. We've done the substitution step. Step 3 is to solve for one coordinate. Now, it's not always x or not always y. You just do it based on what's the easiest. So I have to solve this equation. Now, I've taken 2 equations. Each involve 2 variables, and I've substituted, and y is no longer present. So what that allows me to do is I now have one equation and one variable that represents the situation. So 7x comes down to the right. Negative 2 times negative 2 is positive 4x. Negative 2 times positive 4 is negative 8 equals 3. So distribute is the first step. I'm solving for one of the coordinates for one of the coordinates. Okay. And then we got to combine like terms, so that's 11x minus 8 equals 3. Add 8 to both sides, 11x equals 11, and x equals 1. So we found our first coordinate. And now we move on to step 4. Okay, step 4 is to find the remaining coordinate for our point, because remember, our solution is a point. And how we do that is you take x, right, and you plug it back into one of the two equations. It does not matter which equation you use. It is fine to use either, but you can be strategic here, and you should try and plug into the one where math is going to be the easiest for you to use. So let's go ahead and use the top one because we're already solved for y, and that is the variable that I am interested in. So we're going to rewrite this now as y equals negative 2x plus 4, except instead of writing x, don't mind, Pop is up there probably cussing up a storm at a football game. Don't mind him. Okay, negative 2 times 1, that is y equals negative 2 plus 4, y equals 2. So our solution, I'm going to write it nice and big, x goes in the x slot, y goes in the y slot. Our solution is 1, 2. And hopefully I didn't over-explain that. But we're going to follow those 4 steps. I'm not going to write them anymore. I am going to say them verbally so you know what I'm talking about. And I'll try to do them in the same colors as well. The isolation step, the substitution step, and then the 2 solving steps that are left over. Okay, let's go ahead and begin. And I'm going to do the next 3 examples pretty quickly, and I'm going to not explain them as much just so you can see the process unfold. Or I'll try not to. Pop is getting heated watching the football game. Don't mind Pop. Okay, here we go. Let's talk strategy. Step 1 is to isolate a variable. Guess what? X is already isolated for us, so it's done. Step 2, in red, is to substitute. So I'm going to take the thing that I've isolated, x. So let's say I know x, right? X equals 3y plus 7. So I'm going to take the 3y plus 7 that it is equal to, and I'm going to merge it with the second equation. You always need to use both equations in order to find the solution, right? So I'm going to take what x is equal to, and I'm going to replace it down here, and we'll end up with 3y plus 7 equals 2y minus 1. Now these parentheses are just kind of to show that I've substituted. They really have no merit in the problem. You're distributing, right, a 1 or something, so it's not going to change anything. So this is 3y plus 7 equals 2y minus 1. Let's go ahead and combine like terms. They are on opposite sides here. So I'm going to subtract the 2y from both sides. That's going to cancel. You'll end up with y plus 7 is equal to negative 1 minus 7 minus 7. Y equals negative 8. Okay, so we have just, oh man, I used the wrong color. That was our substitution step. This is all supposed to be in green, so I'll just note it like this. This is step 3. Okay, and then let's move on to step 4 in blue, which is to plug this back into one of the equations. It really doesn't matter which one. I'll use the bottom one this time. So we'll say x equals 2 times negative 8 minus 1. So x is equal to negative 16 minus 1, which is negative 17. And we have our solution. So please state your solution as an ordered pair. It is negative 17 comma negative 8. Hooray! Okay, let's do a couple more. So in the next ones, x is not necessary, or the variables are not isolated for you, so you have to kind of strategize. So with this one, in order for us to solve this system, we're going to have to isolate for one of the variables. Now, you can do it with any of the variables. You can isolate any of them, but one of them is much, much easier. Most students don't like fractions, so I would advise you to avoid fractions if possible. So here's what I'll do. I am going to solve for the one that is not going to create any fractions. Step one, any of if you can spot a term. So by the way, we could solve for x in the top, y in the top, x in the bottom, y in the bottom. Turns out solving for y in the bottom is the easiest because it has a coefficient of -1. When we move it to the opposite side, it will have a coefficient of 1, and we will have solved for y. So I'm going to add y to both sides here in my isolation step and get y equals 2x. Now, we didn't have to do this in the previous examples because it was solved for x there and it was solved for y there, and so we were done, right? So let's go back. So isolation step complete. Let's go to the substitution step. I used the second equation here, so now I have to plug it into the other equation. So this is step 2. So I'm going to rewrite the other equation, but instead of writing y in the top equation, I'm going to write what y is equal to, which is 2x. So we get 4x plus 3 times. Okay, and then we're going to come around here. I'll plug in 2x because that's what y is equal to. Now we move on to step 3, which I am going to do in green this time. We're going to solve for x. So first I'm going to take care of this multiplication. So simplify the left-hand side. 3 times 2 is 6x equals 0. 4x plus 6x is 10x equals 0. So divide by 10 and we'll get 10 times what number? 0? 0. Alright, so we know that for our point, the x-coordinate is 0. We don't know what the y-coordinate is yet, but we can plug it in and solve. Alright, so plug it into one of the two equations. It doesn't actually matter. You can also plug it into the one you solved here at the top. That's the easiest, so y being equal to 2 times 0. Well, 2 times 0 is 0, so that kind of gives us our answer. But let's say we didn't see that, and I use the top equation. 4 times 0 plus 3y equals 0. 4 times 0 is 0 plus 3y equals 0. 3 times what number is 0? Well, or divide by 3. 0 divided by 3 is 0. So there we get our second point, and that's our solution. Alright, last one. I think it's the last one. Yeah, it's the last one. Alright, look and see what is the easiest thing to solve for here. In purple, isolate. The easiest thing to solve for is the one with the coefficient of 1. That would be this one here. So let's go ahead and solve for that, and we'll get we'll subtract 2y from both sides. X equals -2y plus 1. -2y plus 1. Go to the substitution step. We have to use the top equation. That's 3 times -2y plus 1. Plugging that in. Plus 2y equals 4. So I solved in the bottom equation. Now I'm rewriting the top equation, but I'm taking that -2y plus 1 and plugging it in there. Okay, and now we can distribute and solve for y. Distribute 3, we end up with -6y plus 3 plus 2y equals 4. Combine like terms. -4y plus 3 equals 4. And subtract 3, subtract 3. -4y equals 1, and y is equal to -1 over 4. So, do you remember how I said that? The advantage of doing it algebraically is you can figure out, right? You can know when you have these spots where it doesn't cross on a grid line, you can know exactly where that is, whereas graphing we'd kind of have to guess. Not if we're using algebra here. So now I'm going to switch to blue, and we're going to do the last step. So let's be smart about kind of how we're solving this. Okay, let's go ahead and plug this in. Alright, I'm going to plug it into, let's just do the top equation, x plus 2 times negative 1/4 equals 1. 2 times 1/4, or 1/4 of 2, is equal to, since this is a negative number, negative 1/2 equals 1. So x is equal to, add 1/2 to both sides, 1.5. Alright, cool. I'm going to do the previous problem one more time on the next page. I'm going to pause it and copy the video really quickly, or copy this slide. I'm going to do it one more time, and I'm going to do it the hard way. Maybe not this one. Let's just do this one again. I'm going to do this one and not solve for x, just to show that the process still works and we'll get the same answer. Okay, so technically we're done here, but yeah, I'm just going to do this really fast. Let me pause the video. All right, so I pulled this up in Desmos just so you can see it. There's the example we were just looking at. It has a solution of 1.5 comma negative 1/4 like we predicted. Let's do it again, and let's assume we didn't solve for the easiest one, the one with the coefficient of 1. Let's instead solve for one, like let's do one of the harder ones, like maybe let's do something disgusting. I'm going to do the 3x here. Is that right? Let's change our full screen. Let's say we solve for, let's do y in the top. Let's say we solve for y in the top. It's not the easiest one to solve for. I'm going to do it anyway. So we're going to isolate. You'll get 2y equals negative 3x plus 4. I just want you to know that it's still doable. Divide both sides by 2. You'll get negative 3 over 2x plus 2. Okay? Now you can take that and we can substitute it into the bottom equation for step 2, which will be x plus 2 times negative 3 half x plus 2 equals 1. So I rewrote the bottom equation, but I substituted in. We can now distribute and solve for step 3. And you don't have to number these steps or anything. Like, just do the problem. It's fine. Distribute the 2, and you'll get x plus negative 3x. 2's cancel, and then plus 4 equals 1. And you'll get negative 2x plus 4 equals 1. And then subtract 4 from both sides. Negative 2x equals negative 3. Divide both sides by negative 2, and you'll get your 1.5. So there's our 1.5. And then if we plug that 1.5 in, it's 1.5 comma something. We don't know what that something is yet. Plug it in. Let's just do the bottom equation. So that'll be 1.5 plus 2y equals 1 minus 1.5 from both sides. 2y equals negative 0.5. Divide by 2, y is equal to negative 1/4. Hey, we did it, team. All right, hope that was helpful. That was a review of solving systems of equations by graphing and solving systems of equations by substitution. Hope you liked it. We'll see you next time.